Okay. Okay, please.
Do you see it?
Yes.
Okay. Hi, everyone. I'm here to present my our paper on the decidability of a fragment of preferential LTL. The plan goes as follows. We're gonna highlight, in a sense, our field of study on the work we've done on preferential linear temporal logic, and some questions that we had concerning the statisticability problem of our logic, and we concluded with some future work that we can do. We are doing so at the moment. So temporal logics, as you may all know, is a family of formalisms that helps us represent and reason about propositions that can vary in time. It found an extensive application in formal verifications of systems, computer systems, and in AI too. What we noticed is that although they are successful, systems are not, by definition, 100%. That we can have some exceptions that are that arises from our systems. The limitations of classical temporal logic is that we cannot represent or reason about systems that can be lenient toward exceptions. What we like to do is integrate non-monotonic reasoning, which is a pillar when building systems that are lenient with exceptions. It was heavily studied in the case of propositional logic, model logic, and descriptive logic. Our goal here is to apply non-monotonic reasoning to temporal logics. Here's an example of what we would like to do. We have a computer system that that checks the value of a variable during each iteration. We can see that we have some states that are benign, in a sense that we, if there is an exception that rises from these from these time points, we would like that our verification continues. So in a sense, if we have always x superior to 3, we will have a false state. We have false, but we would like to have a weakened version of our the operator always that can return the true value in this request. So yeah, so our goal is to have an extension of LTL that can express preferences of an action. We do so by integrating what we call non-monotonic operators. We will see that in the upcoming slides. So just to set up the notation here, for LTL, we represent LTL as an infinite succession of time points that are marked with natural numbers, or the sequence of natural numbers. The interpretation is a mapping function that associates each time point with the value with the set of atomic positions that are valued true in that time point. The box alpha means that from the time point and all its successors, the alpha holds. Diamond means that there is a successor within this timeline which alpha holds. What we would like to integrate to LTL is the preferential model proposed by Krauss, Lehmann, and Megiddo. They added to their they added a preference relation, which is a binary relation that can order different words in from the least plausible to the high likely outcome. So if we see S1, 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 S2 in here, as shown on the slide, means that S1 is more preferred than S2. So if we have a preferential entailment of the sort, beta is a preferred entailment of alpha, means that from the most likely or most desired words that satisfy alpha, we can conclude beta. So what we propose in our logic, in terms of grammar and in terms of vocabulary, is that we have a finite set of proposition, Boolean connectives, temporal operators, and the introduction of two operators, non-monotonic box, which signifies preferably always, and diamond, a non-monotonic diamond, which means a preferred eventuality. They are both a unary operators which act like their counterparts. When it comes to interpretations for our logic, is the same. We have a temporal structure which is represented by a sequence of natural numbers. We have a valuation function that associate a set of atomic proposition to each time point, and the preference relation, which is a binary strict partial order on the elements of our time points. So if we see a box, non-monotonic box alpha, that means all the preferred time points with respect to our preference relation, the statement alpha holds. For a non-monotonic diamond is if we have a preferred future with respect to our preference relation, the statement alpha holds. Here's an example of an interpretations. We have the set of our atomic propositions. We have this the set of preference expressed by the reasoner, and we can see that the time point 2 here is not preferred in the interval from O to infinity, because there is a time point which is 0 that is more its results are more desirable than 2. So we can see that we have the preferred states in our structure, which are 0, 1, 3, 4, and 6 from and 6 to the infinity. We can see that always P does not work, does not hold, but non-monotonic box of P holds in this interpretation. We also worked on the Decidability problem of our language, which is the question: is the Decidability of LTL tilde the sentences are is the Decidability of LTL tilde decidable problem? We've done our first fragment of the language, which contains only the Boolean connectives, box, diamond, and their non-monotonic counterpart. And we also made some restrictions on the preference relation. The theorem is as follows. If alpha is satisfiable in our interpretation, then there exists a model that that is bounded in on its size. So what do we mean by state-dependent interpretation? State-dependent interpretation means that we have the constraint that each pair of time points that have the same evaluations express the same preferences. The goal here is that we have a more we have an interesting property, is that if we find that a time point is highly desirable, and if we find it in the future, but both of these are highly desirable in the reasoner's mind. We can see, since we are working with finite set of propositions and having an infinite number of time points succeeding, that we can split we can split any interpretation into two parts: an initial part and a final part. The final part is have a subset of distinct evaluation that replicates infinitely many times. So we can compute the size of our interpretations by adding the length of the initial part and the number of distinct evaluation that exists on the final part. I would like to add also the acceptable sequence is a notion proposed by Sisler and Clark on their proof for complexity of normal LTL. The general purpose of it was just from an initial interpretation, we can take time points as such that the resulting interpretation have strictly inferior have an inferior size from its predecessor. So what we do generally, that if alpha is set, how we made our proof is that if alpha is satisfiable, we can find an interpretation that satisfies it. Then we can extract an acceptable subsequence that still satisfies the same sentence. And finally, we have the resulting interpretation. The main result of this paper is that we can always, if alpha is satisfiable, we can always find from any starting interpretation, we can always bound it in size.
2 minutes left.
Okay. So the second thing, now that we have our theoretical bound, is that we can guess a model thanks to this notion of UPPI, which is just a representation of the initial part and the distinct evaluation of the valuations that exist in the final part. We guess this structure and we verify whether it satisfies alpha. If it doesn't, we guess another one until we find the right one. And this is how we showed that this fragment is a decidable problem. So yeah, just to recap, we introduced a new approach to LTL that has the ability to express the preference between our time points, and we determined that the fragment that we discussed above is a decidable problem. what we're working so far that we have now that we have our theoretical bound, upper bound, is that we would like to have a Tableau method for our language. We would like also to add more temporal, more non-monotonic, non-monotonic temporal operators to our language, and finally introduce the conditional entailment to LTL. Thanks for your time.